Okay. All right. Okay. It's okay. But all right.
Okay. We have Zhuowen here, who is a full professor at UCSD. Before that, he was a professor at UCLA and also really working at some research Asia. His research actually was worked for a couple of prizes. One of them was a Bayesian prize. And we are very much looking forward to hear from him about more or less diffusion models.
Okay. Yeah. Thank you for the introduction. So let's directly get to the talk. Yeah, thanks everyone to be here. And also Kai Ming's talk gave me a very good perspective in terms of how to lay out the talk. So basically, do we want to be more or less Bayesian in today's world? Trying to bring back the perspectives of both generative models and discriminative models, like in Kai Ming's work and talk, he's showing like in terms of this reconstruction versus classification. Okay, so quickly get to the point. So I'll try to touch base on 4 aspects quickly. Hopefully there's enough time for me. So basic kind of Bayesian formulation, Alan is here. So he's one of the pioneers in computer vision. Back then was kind of amazing. I still remember when maybe he submitted a paper to CCV or CVPR, they are using Bayesian. The reviewer come back with the review comments, oh, they're using Bayesian for computer vision. This is so novel. And we should accept the paper. But nevertheless, so the whole thing Bayesian was given like by studying the posterior distribution given data X, we want to study Y, and typically as being separated into likelihood and a prior. Later on, of course, in modern machine learning and AI, we replace the likelihood with a direct posterior distribution as a data-driven approach, which we'll talk about later. And this is the basic kind of formulation. And I borrowed the slides from Alan. And basically back then, and suppose you to see a 2D image like this. These are 2D images. And then you want to infer what it will be the 3D hypothesis, which is Y, to make the projection for this 2D image. And then you see all these are the hypothesis spaces that you want to roll out to pick which one will give you the best result. And the Bayesian formulation says, so out of all these hypotheses, these competing hypotheses, there are 3 possibilities that will result into the reconstruction of this 2D image. In the end, clearly we have some prior about the possibility of 3D kind of shapes. These are 2 pretty much that we don't see often, where this one is more like the thing we have. So if we put a prior on top of this distribution, then we can obtain our solution. This is basic kind of Bayesian inference from back like 30 or 40 years ago, which was inspiring. So if you look at this one and you listen to Alan's talk, you say, oh, of course, everybody wants to be Bayesian. So that's what motivates us to do. So in early stage, kind of the development of computer vision, object recognition, or machine learning was relatively small scale data sets. The top-down prior can therefore provide a strong regularization and inductive bias to the bottom-up process that's being trained from relatively small scale data. So that was pretty much the state we had. And then we and with Zhu and also you and Alex Chen, we together have this line work trying to do the DDMCMC, hoping that the top-down part can guide the process. These processes can be kind of decomposed into a number of steps in terms back then segmentation, image parsing, splitting, segmentation, like merge, even diffusion process back then. Okay, and then this kind of Bayesian formulations, I said it was popular, and then the so-called famous pictorial structure to have these parts. Then you put, if you see a face, of course you have eyes, nose, mouth, and you want to put a prior on top of it such that they form some regularization. So if you have a relatively weak kind of data-driven process, then the prior part, the top-down part will definitely give you some kind of help, a lift in terms of making the inference. And later on, all these kind of probabilistic latent semantic analysis or dirichlet model, part-based models are pretty popular. People learn the parts and then trying to learn a dirichlet model, for example, out of it, trying to combine things together, like a Fei Fei and Antonio Torbola, the group of work. So from that, then let's look at some Bayesian statistics from a generative model kind of sense. So which is my second kind of topic of the talk. So basically, for historical talk kind of thinking, we always consider generative models being the ultimate kind of thing. Suppose you can draw, you can paint, you can generate all the images. The understanding is pretty much almost like a subset that was embedded in kind of the root of the Bayesian people, thinking that once you have a if you can draw, you can almost any images out the world, then you have to be able to analyze them or recognize them. However, discriminant models later on take off for classification. They turn to be easier to train and more objective to some degree. So these are some of the pros and the cons of the discriminant models and some of the pros and the cons of the generative models. So there was like these competing kind of philosophies in terms of building generative models and discriminant models. So back then. And then very early on, in terms of learning generative models, the whole school, especially in computer vision, was guided by or motivated by this Heger-Bergen's kind of principle. Almost most of the generative models were guided by this principle, meaning that suppose you want to synthesize or learn an underlying textual model, and then you want to come up with a few kind of features, and then you compute the histograms out of this image. And then suppose you have a random image, and then you also can drag this image such that the target image has this match the same histograms of the input image. Then you can basically generate a texture pattern. Back then, generating texture pattern wasn't easy at all. So basically, you want to minimize the distance between your given training image and your synthesized image. Back then, using so-called histogram stretching, and you can do that. Almost you can think of as like a modern diffusion model is like to turn noise into a target image. In a spirit, this is done in a kind of deterministic procedure. And there was a procedure, and later on, the same model was developed by Zhu, Wu, and Mumford, building so-called a free model to match the statistics. I want to show you a demo here to show that how non-intuitive it is. Just give me 1 second. I'll switch. This is very simple Python code I wrote. It's very simple. Basically, you generate an image of 300 by 300 and just let every single pixel to be random. So these are the images you can see out of just random samples. So the Earth has probably 4.5 billion years history. Suppose you can take a time machine to travel back to the beginning of the Earth, and you take your laptop with you. Hopefully your laptop battery can last for 4.5 billion years. Then you click a button and let it show the images. And the chance throughout this 4.5 billion years to see a real image, even an image like with edges or something like that, is near zero. That shows how extremely unlikely to see almost any images we can generate out of random samples. So this is why kind of you have to appreciate the underlying statistics. So in Kai-Ming's work, he's showing the flow matching, all kind of the diffusion process, things like that. So that's kind of an illustration. So let me switch back, sorry. So how much, until when, my talk? How much? 20 minutes, okay, thank you. So this is why early pioneering work was non-trivial at all. Even synthesized images like this is extremely unusual in terms of statistics. Okay, so now coming back to this kind of generative models. So in a nutshell, majority of the existing generative models before, I think it was like in 2002 or something like that, it was essentially trying to build a statistic to match so-called empirical statistics from a bunch of training images versus model statistics, such that the average expectation of your statistics from the images you generate can match the target image. So that's kind of the underlying principle. So however, the whole kind of field of generative models back then, again, was dominated by manually designed features. So around 2006, I was asking myself, so can we see something like a generative out of discriminant models? So the idea is the following. So instead of matching statistics to match your training image, can we train a discriminant classifier without being told about any features to match? Suppose you have a target images or target samples. Starting from random noise, you generate some random noise, you train a classifier, you separate them, then you generate adversarial samples, and you train update further. In today's world, it's called a generative adversary, again, a neural network. Back then, neural network was not popular, so this was 2006. So I was trying to study generative models from discrete classifier. So this is very simple Bayesian. Suppose you have an image X, and you want to label it to be your positive. And this posterior can be derived using Bayesian. This is your PX, which can be further expanded using your prior and then conditional probability. Plus, this is joint probability between your X and Y, and further can be decomposed into your prior and this is your prior distribution. Sorry, your targeted distribution. So this is kind of very simple Bayesian. And then if we turn it around, then interestingly, you can see essentially the generative model you want to build, essentially the target distribution can be computed from the prior about your positive and negative, and also your posterior distribution, how likely it is positive or how likely it is negative, and times a reference distribution. So in a nutshell, what it says, suppose you want to learn to speak French, for example. If you can speak perfect Italian, and then you know perfectly the ratio, how likely it is French and Italian, and you can turn yourself from Italian-speaking person into a French-speaking person. So this is from Bayesian formulation. So if we drop the prior part, make it easy, then essentially we have the simple kind of formulation. If you want to obtain a target distribution like a French, you can have Italian, then a ratio, how likely it is Italian and how likely it is French. However, this is a chicken and egg problem. In order to have a perfect French, then you need to also speak perfect Italian, which is equally difficult. However, we can do this in a kind of recursive way by generating initial distribution first, then you train a discriminant classifier, and then you gradually update them until they converge. So I'll just directly go to the slide. So basically, you can iteratively update your target distribution through a kind of an iterative process. I'll show you the high-level thing, and this shows like you can approach the distribution asymptotically. I'll just show you some illustration. So basically, these are some of the dots I wrote. This was a CVPR paper by myself. And basically, you have these single points. Suppose you start from a random noise. These are your original distribution. Then you train a classifier out of it. After you train a classifier, then you obtain samples. This classifier says it's very positive. And then the new samples will be closer to your target. Then if you gradually change it until your target is not being separated by your classifier. It says, I give up in classifying the real given ones versus your generated ones or adversarials. So essentially, this is an energy-based model. The N generative model is just a product of your sequence of ratio of your district classifier and up to a reference distribution, which can be just Gaussian distribution. And then I did the procedure to initially bootstrap, then later on to sample until match the textures. So these are some of the examples I show how to use this idea to train to generate textures, and also to learn a style, Van Gogh style, can turn input image into do artistic style transfer. And you can learn faces, you can learn natural image pairs to do denoising, all these kind of things. So this pretty much laid out the foundation, early foundation of generative adversarial learning, which was followed by GAN and echoed in there. Of course, there's still some difference in the GAN paper versus mine. I was building an energy-based boosting model where they are building using a neural network architecture, and they have an explicit generator and a discriminator. Where here I have a unified kind of energy-based model. But nevertheless, that's pretty much the start of the modern generative adversarial learning literature. But having done that, on the one hand, I'm pretty happy that I can build something like a pretty general to study models of a very large family of kind of patterns, if you will. But on the other hand, the quality is still not that satisfactory. So I paused a little bit. Then back then, trying to see how do we play the role between generative versus discriminative? So is really generative capability that you have superb than discriminative models. And then 2017, we also built a neural network version out of it to turn boosting into neural networks such that sampling can be made easier. So then we have a single neural network being itself generative and discriminative, which is also an energy-based model. That was like a 2017 NeurIPS. And we also have ICCV paper to learn textures using this type of line of work. And then after learning, you can see similar. Now it's not that surprising, and being able to generate images of this quality is no surprise at all. But let's ask a fundamental question then. In the deep learning era, this kind of Bayesian formulation has more or less disappeared. So why is the Bayesian not anymore widely adopted? So this is kind of, again, the Bayesian formulation. Start to put some question on Bayesian, because Bayes told us Bayesian is the ultimate kind of the golden principle to guide the inference process, which Alan still is a strong Bayesian as far as know now. But let's see what's going on in the modern stage. So first, kind of rich features learned from large-scale data become substantially more robust than manually designed one. Strong bottom-up process, learning in XY fashion from paired data that actually do not necessarily have the need to introduce another separate prior, which is hard to learn anyway, because in order to learn pictorial structures, we have to make so many assumptions. And also, we didn't have the strong generative model with a very kind of much really a modeling capability as we can see today. So I think this is why kind of people pretty much forget about Bayesian, and then a lot of the posterior part has been almost naturally included in the data-driven part. For example, recent generative models like classifier free guidance, you can have conditional and also unconditional all together and put there. Then there seems to be a lack of need to have a Bayesian. However, Bayesian diffusion models actually can give us a little bit more hope. Probably I don't need to introduce too much about diffusion models. But one thing particularly, I think, really kind of attractive about diffusion model is it turns one single step into a number of stages. So then coming back to Kai-Ming's kind of point, actually, I kind of disagree with him. Given my years of, I can be wrong, but given my years of experience in generative models, we start from one step kind of thing. So essentially, the reason why diffusion models become so popular is it is getting away from one step generative model. I have an analogy. So for example, if you want to, let's say, come to Nashville, for example, like I live in San Diego. So from San Diego to Nashville, so the original kind of statistician would tell us, in order to do that, you need to draw a map. You know, once you have a map, then you can plan your trip from San Diego to Nashville. However, diffusion model says, no, you guys have been trying to draw this map for so many years, yet it takes so much efforts. I'm not going to draw a map to you, but however, I can tell you, like you can drive for, let's say, every 30 minutes, take this highway and drive for 30 minutes. Then once you land or arrive in the next stop, I'll tell you how to go there the next. So instead of drawing an absolute map, diffusion models trying to actually learn the gradient or trying to give you the explicit instruction, but not an explicit map, that gives us a much significant elevated capability in terms of studying the statistics. And also this gives us hope to bring Bayesian back, because now we have a far more capable generative models that can be combined together with our strong data process. So now we can replace pure Bayesian with some data-driven part. Of course, you still want to see if you can introduce some prior. So if you're not 100 Bayesian, probably you don't like it, but if you're 70% Bayesian, probably it should be okay for the moment. And then we take this single image reconstruction as an example. This is a very unique situation where getting a training set with ground truth, really ground truth shape for real image is really hard. However, we have a lot of existing shape that are independently existing. So this gives us hope to bring back the Bayesian. Suppose we have a strong diffusion process, which is data-driven process to turn your single image into some kind of 3D reconstruction. However, there's no explicit shape that we want to use. Given increase the power of generative models and given all these strong data process, and then probably we can bring back some aspects of analysis by synthesis. So for example, we can learn an individual kind of a prior using diffusion models for these shapes, point clouds, independently. Then this would be a standard Bayesian prediction. You have all these x's. And then you have, suppose given this x, you have this prior distribution. And the traditional Bayesian will come up with a likelihood function and with a prior about this particular kind of y. And the multiplication of this will give us the inference part. This is traditional Bayesian. And then in a stochastic gradient Langevin process, well, like as I said, like you plot out the US map. And then at every step, because you have the US map, you can tell yourself how to go to the next part. So you're learning the distribution, then you will naturally compute the prior. However, modern diffusion-based models will allow us to only to compute the prior without the existing, the explicit knowledge about distribution. Or to some degree, you don't care. All you want to is to, let's say, drive from San Diego to Nashville. You really don't care where Nashville is if your target is to come to Nashville. It may be on the top left corner of the US map, but as long as you can come, then it's okay. So essentially the diffusion model, Bayesian diffusion model can independently train a prior, and then with this integrate the process in the middle, then we can bring back the diffusion process, Bayesian process into the modern diffusion world, where in scenarios where you have rich data in the white space, and also like a high-level thing that you want to inject, then you can naturally integrate them to your existing diffusion models that are being used to learn how to drive, not where to drive. So then we apply this, and this was our last year's CVPR paper, and to perform single image 3D reconstruction. And then we show state-of-the-art results compared to strong bottom-up process, including classifier guidance, where the prior part has been implicitly captured. So this shows that explicitly capturing 3D can help more than implicit in this case. And the process itself is pretty simple. You have two parallel diffusion process. One is prior, and one is your data-driven part. And once in a while, you let them exchange information and fuse, and then your prior part, top-down part, can be used to correct some mistakes that your bottom-up process is making. And then we have two alternatives to do the merging part, and then we show state-of-the-art results. And we can show that the top-down part can indeed be injected to improve the results. Okay, so in the interest of time, I'll quickly get to our very recent work. And I also want to show you another perspective in terms of studying the gap between generative and discriminative. We want to ask the question, do generative models indeed provide complementary information to help with the discriminative classifier? One is a closed set study, another is open set study. And closed set study says both generative models and discriminative models are trained on a given set without seeing any external data. If you go back to 20 years ago, you talk to Alan, they always say generative. Once you have generative, you can almost forget about discriminative because discriminative will come up naturally. That turns out to be not the case based on our experience so far. Discriminative classifiers have been so much easier to train. Okay, so regardless how great the generative models you have seen, you can give a try, all these videos, images, any modern models you have obtained. If you see a real image and also a generated image, you train a classifier, the convergence of your classifier is extremely quick, meaning like you're not going to need to burn your GPU time too much. You can immediately almost get 90% or 99% of accuracy. This also echoes to the demonstration I show you how to generate real images using random samples. The fundamental manifolds or statistics from real and any given, or regardless how high quality the images are, is extremely large. If you would train a classifier, they have lived in fundamentally different manifolds, if you will. So this sounds like a daunting. So regardless of how much efforts we have done, almost like there's no way, I can be wrong, but I expect for the next 50 years, 100 years, there won't be any generative models that can give you real data from statistical models that is really indistinguishable from natural images, just because the space is just so high. However, that said, these fake or these synthetic images are still useful because they also span a common manifolds with real images. This means indeed you still can utilize the synthetic data to help with training your discriminative classifier. So we give a study. First, we study a closed set where these are some medical blood cell images that don't have any language, really language meaning if I tell you basopolysis, I don't know how to pronounce it, you still cannot draw, unlike natural images. If I show you a tiger, you probably can draw tiger images. That limits us from having an image generated from text as a scientific study. We want to see how really complementary is between generative and discriminative model. So these are the models is trained and to synthesize images. From naked eyes, real and synthetic images become pretty close to each other. And then if you would use existing diffusion model using text only, you can see these are the images generated by stable diffusion, which, as I said, because it has no real correspondence between image pattern to the text, so the images are far from these given training images. Just an illustration. you can do on the ImageNet as well. And then I quickly give us the conclusions. So we show if you would use synthetic data to do the documentation to improve your classification, this would be the equivalence of, let's say, 1,000 probably real image is equivalent to, let's say, 50,000 synthetic images. And then we have explicit kind of formulation to tell you the equivalence if you want to improve the results. Of course, subject to different classification results. So these are on the different data sets. And then this is first time study to show the real quantitative equivalence between real versus synthetic. And then to give you a guideline later on, if you really want to use synthetic data, then how much data copy you need to match with the real data collection kind of thing. So this is closed set. And then in the interest of time, I'll skip all these details. Now, we also did the open set. For open set, there are a lot of papers already out there. They are using pre-trained models and using text to generate images, and these images are used as a data augmentation to help. However, most of these are just some empirical studies in terms of classification. None of the work also studied the equivalence between real versus synthetic data. We also give out these explicit kind of equations to show how to match. Again, how many copies of your synthetic data can be used to match your classification results to do image classification to enhance the results. And quickly, observation discussion. So closed set generative model documentation consistently enhance classifier performance, sometimes even surpassing open set configuration. Closed set generative data augmentation exhibits a better scalability as the base training classifier size increases. And with the fixed base training set, the performance gain from closed set to start to diminish as the performance kind of tops. Again, to the best of our knowledge, the first time to show empirical equivalence, quantitative equivalence between real and the synthetic data augmentation for different classification. This shows that because of different model aspects, even from the same given training data set, generative models learned for the purpose of generation still provide something different from pure classification kind of task or objective. This view has been kind of being flipped a couple of times in the history. I think given powerful generative models, it seems like generative model aspects are providing something complementary. A little bit like in Kai-Ming's talk where he shows this classification versus reconstruction kind of thing. Okay, in conclusion, so generative models, especially state-of-the-art modern diffusion models, provide complementary information. Images generated by statistical models span still very different data manifolds than the real images. I said probably for the next 50 or 100 years, there won't be any generative models that can completely generate images that completely like overlap, align with the real images, but I can be wrong. But increasing representation power analysis by synthesis can be brought back. And a Bayesian diffusion model type of thing is a new statistical inference model that actually highlights a lot of kind of future promises in a right domain. Okay, all right, thank you for your attention. Yeah, be happy to take questions.